Hi students, I am Praveen Sebastian Paul. In this lecture we are discussing an intrinsic semiconductor. The semiconductors are divided into two types. Basically they are intrinsic semiconductors and extrinsic semiconductor. The pure form of the semiconductor is known as intrinsic semiconductor or pure semiconductor, and semiconductor in which intentionally impurities are added for making it conductive is known as extrinsic semiconductor. The conductivity of intrinsic semiconductor becomes zero at room temperature, while the extrinsic semiconductor is very less conductive at room temperature. An intrinsic or pure semiconductor is also known as undoped semiconductor or I-type semiconductor. It is a pure semiconductor without any significant dopant species present. The number of charge carriers is therefore determined by the properties of the material itself instead of the amount of impurities. In intrinsic semiconductor, the number of excited electrons and the number of holes are equal, that is, N is equal to P. This may be the case even after the doping of semiconductor, though only if it is doped with both donor and acceptor equally. In this case, N is equal to P still holds and the semiconductor remains intrinsic though doped. The electrical conductivity of intrinsic semiconductor can be due to the crystallographic defect or electron excitation. In an intrinsic semiconductor, the number of electrons in the conduction band is equal to the number of holes in the valence band. An indirect band gap intrinsic semiconductor is one in which the maximum energy of the valence band occur at different k, that is k space wave vector, than minimum energy of the conduction band. Examples include silicon and germanium. A direct band gap intrinsic semiconductor is one where maximum energy of the valence band occur at the same as minimum energy of the conduction band. The examples include gallium arsenide, and a silicon crystal is different from an insulator because at any temperature above absolute zero, there is a non-zero probability that an electron in the lattice will be loose from its position, leaving behind an electron deficiency called a hole. If a voltage is applied, then both the electron and the hole can contribute to small current flow. The conductivity of a semiconductor can be modeled in terms of band theory of solid. A band model of a semiconductor suggests that at ordinary temperature, there is a finite possibility that electrons can reach the conduction band and contribute to the electrical conduction. The term intrinsic here distinguish between the properties of pure intrinsic silicon and the dramatically different property of a doped N-type or P-type semiconductors. An extremely pure semiconductor is called intrinsic semiconductor. On the basis of the energy band phenomenon, an intrinsic semiconductor at absolute zero temperature is shown in this figure. Its valence band is completely filled and the conduction band is completely empty. When the temperature is raised and some heat energy is applied to it, some of the valence electrons are lifted to the conduction band, leaving behind hole in the valence band as shown in this figure. The electrons reaching at the conduction band move randomly. The holes created in the crystal are also free to move anywhere. This behavior of the semiconductor shows that they have a negative temperature coefficient of resistance. This means that the increase in temperature, the resistivity of the material decreases and the conductivity increases. So my dear students, the electrons and holes are important in the case of a intrinsic semiconductor's conductivity. In an intrinsic semiconductor such as silicon, at room temperature above the absolute zero, there will be some electrons which are excited across the band gap into the conduction band and which can support the charge flow. When the electron in pure silicon crosses the gap, it leaves behind an electron vacancy or a hole in the regular silicon lattice. Under the influence of an external voltage, both the electron and the hole can move across the material. In an N-type semiconductor, the dopant contributes extra electrons, dramatically increases the conductivity. In a P-type semiconductor, the dopant produces extra vacancies or holes, which likewise increases the conductivity. It is, however, the behavior of a p-n junction which is the key to the enormous variety of a solid-state electronic device. So, my dear students, next we should discuss what is a semiconductor current. The current which will flow in an intrinsic semiconductor consists of both electrons and holes. That is, the electron which have been freed from their lattice position into the conduction band can move through the material. In addition, other electrons can hop between the lattice position to fill the vacancies left by the freed electron. This additional mechanism is called hole conduction because it is as if the holes are migrating across the material in the direction opposite to the freed electron movement. The current flow in an intrinsic semiconductor is influenced by the density of the energy states, which in turn influences the electron density in the conduction band. This current is highly temperature dependent. So, my dear students, in this lecture we had just introduced the term intrinsic semiconductor. The intrinsic semiconductor is the purest form of the semiconductor, and the conductivity of the intrinsic semiconductor becomes zero at room temperature. And also, this intrinsic semiconductor is also known as undoped semiconductor or I-type semiconductor, which is a pure semiconductor without any significant dopant species present. The number of charge carriers is therefore determined by the properties of the material itself instead of the amount of added impurities. So, my dear students, hope you had understood this topic. So, dear students, kindly go through the assignment question. Our question is, write notes on intrinsic semiconductor. So, my dear students, in the upcoming lecture, we will discuss the extrinsic semiconductor. So, as we mentioned, an extrinsic semiconductor is one that has been doped. That is, we had added some impurities into the semiconductor in order to apply the semiconductivity property. So, dear students, see you soon. Until then, goodbye, thank you, and all the best.